So yesterday we started our notes. This is on page 3, by the way. So we are on page 3 right now in your note packet. Yesterday we started out with having a drawing of H2O right here. And we use that to kind of refer to, for a lot of this stuff, the basics, right? So we said that for covalent structures, we're now doing Lewis structures, okay, covalent compounds. The atomic symbol has to be present, so we had to have our letters, just like when we were doing electron dot notation. And your atomic symbol, sorry, that was it. Your atomic symbol, so your letters had to be present. Your dot pairs or dashes between two elements represent a shared electron pair. In your final answer, you used a line to represent the shared pair. So meaning, if we have a line between two elements, that's showing how many electrons. How many electrons get shared?
2.
Only 2, exactly, okay? So the line represents 2. That is super important to remember, okay? Each line represents 2. Dots that are only attached to one of your atomic symbols are unshared electrons. So up here on oxygen, I had 1, 2, 3, 4 electrons. If you notice, they were in pairs. The unshared pairs are called lone pairs. Okay, and they are not involved in the bonding, and they only belong to whoever they were attached to. Those pairs come from, it's important, they come from when you first drew out your electron dot notation, right? Oxygen had 1, 2, 3, 4, 5, 6 valence electrons. Those 2 were already attached to oxygen to begin with. The 2 single ones turned into bonds. Do you guys see that? Okay, so it's going to come from you drawing that initial electron dot notation. All right, so let's keep going. Single bonds. Single bonds are only one pair of electrons that are shared between the atoms. They're represented by 1 dash. So an example of that could be maybe fluorine gas. We would have F connected to F, okay, just one single line, and then you would have to have their lone pairs all around them. Okay, so one line. A double bond is something that has 2 pairs of electrons, or 2 dashes. So an example of that would be oxygen. Okay, so oxygen, we could go 1, 2, to another oxygen, and that one would go like this. So once again, the 2 lines in the center represent the double bond, but once again, the whole lone pairs on the outside come from the initial drawing, right? Do you guys see that this one had 2 bonds that were coming from it anyway? We're just now seeing that they're double bonded together, okay? All right. So the common ones for double bonds are going to be something like oxygen or sulfur. And if you look at your periodic table, what does oxygen and sulfur have in common?
They're on the same group.
They're in the same group, exactly. Oxygen and sulfur, they both have 6 valence electrons. They're in that same family, okay? So that's why anybody from group 16, really, okay? The other one that we're going to add to this is carbon. Carbon can also double bond. You'll usually see a double bond with one of those 3. Okay, so triple bonding, okay? Triple bond is the sharing of 3 pairs of electrons, and it's going to be represented by 3 dashes. Right? Who would have guessed? Triple. All right, so your most common elements for this. It's going to be one that has 3 single electrons. Which one on your periodic table has 3 single electrons, do you think? 15. Group 15 is absolutely correct. So something like nitrogen. So if we had diatomic nitrogen, we would have N, 3 lines with N, and we put our 2 lone pairs on the outside. Again, this is coming from the idea that nitrogen, when it's drawn individually, looked like this. That shows you 3 bond areas. Okay? So most common would be nitrogen. You could choose anybody from group 15, so phosphorus. So I would say P. And then carbon again. Okay, nitrogen and phosphorus
What's the exception?
and carbon.
What's the exception for carbon?
What's the exception for carbon?
Why is it so special?
Why is it so special? Because carbon, when it's by itself, has 1, 2, 3, 4 bonding areas. So it can double bond, it can triple bond, it can single bond. It's the most friendliest family up there, carbon family. So carbon and silicon will both have that capability. 14. Well, no, because once you get below the metalloids line, you're dealing with a metal, right? All right, so next. Okay, so those are the different types of bonds. We have single, double, triple. Easy? What does each line represent? How many electrons? No. How many electrons are in each of these lines?
2.
Do you guys agree? Are you guys just waiting for him to answer? Yeah?
Oh, which one?
How many electrons are represented on this line right here?
1. 2.
Are you guessing?
Yeah.
Okay, thank you for your honesty. So each line represents 2 electrons. So right here, how many electrons are right here? 2. How many are right here? 4. How many are right here? 6. Good. Okay, good. Because we're going to come back to that idea. You got to cover up one letter and count how many electrons you have around it. Actually, before we go on to this next part, let's do that real fast. Around nitrogen, how many electrons does he have? Look at it very carefully. Huh?
Oh, I thought she was crying. I don't like that. 1.
You guys, what does each of these lines represent? How many?
6.
2. So we have 2, 4, 6
And plus 2.
is what?
8.
8. Good. Why are things bonding together? Why do we even have bonding?
So you can share.
Well, because ionic bonding, they're transferred, right? So it's not about sharing. What is the ultimate goal of bonding? To get to what? 8. To get to a full outer shell, right? Do you guys agree with that? You want to have a full shell. If you remember last chapter, so this is before winter break, this was what we had written at the very top of our packet. We said goal for bonding is 8 valence electrons, no matter what. So no matter what, everybody's trying to get to noble gas status, right? Everybody's trying to get to a full octet. All right, so what we just saw here is nitrogen did that over here. If we cover up that one, this nitrogen did as well. If we look at this oxygen up here, 1, 2, 3, 4, 5, 6, 7, 8. So ultimately, everybody has to end up with 8. So I'm going to strongly encourage when you guys start drawing your own, you do this little cover up thing. Cover up each letter to make sure they ended up with 8 electrons around them. How much does each line have?
1,
2. Okay, don't forget that. All right, I'll ask you guys again in a second. So determining the central atom. So, how did I know that oxygen went in the center? Okay, that's what we're answering right now. It's often going to be the unique atom. Do we know what unique means?
Means you're not like everybody else. Like
Right. Yeah, you're one of a kind, right? Different. All right, so it means you only have one atom of that element. So in this situation, H2O, I had 2 H's and then 1 O, so that was the one that went in the center. Okay. It's also usually the least electronegative element, but rely on the other ones because that's easier than looking at the chart, right? But you can always rely on the chart if you want. The other one is if carbon happens to be present, then it is it. Okay? Carbon, carbon, carbon. You will see that one a lot. Okay? If carbon is an option, put them in the center because, back to this idea, it has 4 bonding areas. And it only makes sense to bond all the way around, right? Or do a triple bond or a double bond, whatever. Okay? Put carbon in the center. It's the friendliest element out there. All right.
Why is carbon the friendliest one?
Because it has 4 bonding areas. So if you think of those as hands, It has 4 hands that you can hold, right?
Yeah, but I don't
The
have
friendliest
I don't have
one.
to hold 4 hands.
Well, that meaning like it can hold it with 4 different people.
Oh.
Yeah, crazy, right? It's the friendliest one. All right, so looking at number 4. 4 says something will never ever be central. All right, looking at this, can hydrogen do anything else except for this bond? I want you to think about its valence electrons. How many valence electrons does hydrogen have? It has only 1, right? So it's H and it has a dot. That's it. Meaning it bonds and it's done. So, should hydrogen ever go in the center?
No.
No, it's not the friendliest one. It just shows up everywhere, all right? So hydrogen will never, ever, ever be central. There's also one more group on our periodic table that will never be in the center because it can only bond in one place. Any ideas?
Noble gases.
Not the noble gases, but they're right next to them.
Oh, group 17.
Group 17, exactly. So group 17, don't put them in the center. All of 4, put these on the outside. Okay? Because they only bond in one spot and then they're done. Okay? Can't do much more than that. So, for example, for group 17, I'll just do iodine. Iodine happens to look like this, right? It has 7 valence electrons, so it's 1, 2, 3, 4, 5, 6, and 7. It bonds and it's done. You can't do anything else with it. So don't put them in the center or else you're going to be confused of where you put another bond. There's no bonding areas. Okay. So the last thing we're going to have to always check for is kind of what I was showing you by covering up some of those letters. And that is checking for your octet. So I'm going to write the word octet on this line. It's a tiny little line. I'm so sorry. Octet. Yes. Octet meaning has the right number of valence electrons. The reason why we have to say the right number of valence electrons is because you do have exceptions to that. Most of the time, what does the octet mean? How many? 8. So most of the time, it's going to be the number 8. Your exceptions are these guys right here. Okay, so I'm just going to write them. So 8 usually, but we have hydrogen. Hydrogen has 1 bond, and it's done. How many is that?
2.
Only 2. So hydrogen has a maximum of 2. Okay. This one should bother you because you're like, that's a metal. I don't understand why we're even dealing with metals. Exactly. You're only going to see it every once in a while, so we might as well write it down. I will supply these numbers to you if it comes up, okay? So you don't have to worry about totally having these memorized. All right, beryllium is 4 because it bonds in 2 areas and it's done. The other ones are boron and aluminum. These guys are in group 13. Now, aluminum should bother you because, again, you're like, metal? Why? It's just going to show up. Be ready for it. Those guys only do 6. 1, 2, 3, bond in those 3 areas, and they're done. Okay? Those are the only exceptions. Everything else is what number?
2. No.
These guys are the only exceptions. What is the number for everybody else for knowing if it's their full?
8.
Octet, 8. Okay? All right, so you are now set up for success. Let's try a couple. So, NH3, right here, this first example. NH3, who's going to be central according to these little rules that we just wrote down? Nitrogen. Why?
It's not hydrogen.
Because it's not hydrogen, and because it was the unique one, right? Not hydrogen and unique. Okay, so I'm going to go ahead and we're going to draw this one out. I'm going to scribble out this NAS thing. We're not going to be doing that anymore. Okay, so for NH3, this is your process that you're going to be doing. Okay, we had to figure out who was the center. You guys just told me nitrogen. You're absolutely correct, so I'm going to put a check mark above that so that I know nitrogen's going to go in the center. Then you want to draw out your Lewis dot structure so that you know what each one has. Single electrons will turn into bonds, right? Because do you agree? Like, it's like each of them, if they have a hand, then they're going to hold somebody else's hand, right? So if each one has the hand sticking out, they're both going to hold hands, right? If they are doubled up already, then they're like this. You're not going to hold that hand. You can't just tear their hands apart. Sorry. Okay? So nitrogen had 5 valence electrons, so we're going to go ahead and say, and by the 5 valence electrons are still coming from the top of our periodic table, right? Group 15, take away the 1, it's a 5. So nitrogen is 1, 2, 3, 4, 5. I know each hydrogen has how many valence electrons?
1.
They only have 1, right? So I'm going to say hydrogen with a 1, hydrogen with a 1, hydrogen with a 1. All right, now we have to make these pictures work. I've seen this taught 2 different ways. One way is connect your dots, right? So connect all your dots and you're like, okay, yeah, so I get the main idea, cool. And then they just make it pretty. You are more than welcome to do that. The other way to do it is, you know, nitrogen is your center, so I'm going to go ahead and go nitrogen. I'm going to draw it just like I had up here. 1, 2, 3, 4, 5. I'm going to say single electrons, we know we're going to turn into holding hands or bonding, right? So bond, 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 and I'm going to stick all the hydrogens with them, and it's done. We didn't draw any extra electrons, so we don't need to add anything else to this picture. That's your answer. Okay. One last example. I'm going to do this one, CH3I. Okay. Do you guys have any questions? Do you need me to pause for a second? We're all good?
Well, going back to the types of covalent H3 has hydrogen, right?
You have 3 hydrogens. Mm-hmm.
So how come it doesn't have 3 bonds?
There's 3 bonds right here. 1, 2, and 3. So the double and triple bonds come from how many spots they have. Nitrogen had 1, 2, 3. So if something else had the capability of being triply bonded to it, so if I had nitrogen and phosphorus, they could do a triple bond. They both had 3 spots. Hydrogens only have 1 spot, so these all have to be single bonds. Okay? So this little list that we made over here of most common, it just means that it will show up possibly. But it doesn't mean every single time nitrogen bonds has to be triple bond. Does that make sense?
Yeah.
Okay. Good question. All right. For this one, we have carbon, hydrogen, and iodine. Who's going to be our central one? Why? If carbon is an option, pick it. Never pick group 17, right? Okay? But you guys need to start taking risks and answering, all right? Or otherwise, we'll things can get kind of crazy in here. All right.
That say if you never take risks, you'll never go anywhere.
No, but I say, I forget what I say. I say something else.
Oh wait, we gotta hurry up so we can.
Yeah, sorry. All right, good point. All right, so it is going to be carbon. If you were ever given the option of carbon, you pick the most friendliest element up there. Carbon. Got it? All right. So carbon has how many valence electrons in group 14?
4.
Okay. 1, 2, 3, 4. Hydrogens. How much do those guys have? Just 1. 1. Have another 1. Another 1. Did you guys understand in the warm-up, by the way, that these dots are movable? It doesn't always have to be at the top. Okay. I hope you guys are catching on to that, and maybe I need to get in the habit of drawing it like all over the place. Me saying start at the top, right, bottom, left is to get you to go in a circle. So as long as you're going in a circle, you're fine. All right? Okay.
You're fine.
You're fine. All right. Iodine had
What?
7. So 1, 2, 3, 4, 5, 6, 7. Okay? All right. So carbon is in the center. So you can do, just like we did last time, you can either connect the dots real quick and say, okay, I'm going to fix this up and make it pretty. Put the single dots all together. Or draw who you said was going to be in the center. Make those all lines. And now start putting your outside guys on there. So H, H, H. They don't get anything else because they only have that single dot. I, on the other hand, had that single dot, but then they had these 6 extra dots. Do you guys see that? You got to add them to the image. So we're going to say 1, 2, 3, 4, 5, 6. And now it's done. Okay, checking on the octet. I would cover up this, right? Okay, what does this line count as? 2. 2, 4, 6, 8. Up there, hydrogen can only have 2. Bond and done. Bond and done. Bond and done. The carbon in the center has how many around it? Has 8 around it. 2, 4, 6, 8. Okay?
1, 2, 3, and 4.
Oh my gosh.